Hello everybody, my name is John Maines, and this is my presentation on the nitrogen cycle and the Bobcat Fire in Monrovia, California. So, to start off, the Bobcat Fire. Now, the Bobcat Fire ignited on Sunday, September 6, 2020, near Cogswell Dam nestled in the Bobcat Canyon of the San Gabriel Mountains, and it ended up growing to over 116,000 acres. Now, this fire spread into several communities in the foothills of the San Gabriel and Antelope Valleys, including Monrovia, Arcadia, Sierra Madre, Bradbury, Altadena, Duarte, and Pasadena, as well as communities in the Antelope Valley such as Juniper Hills and Pear Blossom. The figure below shows the Bobcat Fire range, including my home community, which right where it says Monrovia Wilderness Preserve is where firefighters fought hard to stop it from entering the city itself, and contained it to our preserve and the canyon park. So back behind me here is Monrovia Canyon Park. This is where is my home community, and this is where the fire really affected my home community, and it really affected me personally. The fire entered into the Monrovia Canyon Park from the hilltops way up there, and it burned up to 270 acres of Monrovia Canyon Park and the hillside areas up there. Luckily, thanks to our firefighters, no lives were lost and no structures were damaged other than some minor smoke damage. Behind me here is where one of the burn scars was after the fire hit Monrovia and Monrovia Canyon Park. After 5 years, as you can see, it has fully regrown with vegetation, as many other areas in Monrovia have as well. This is likely due to a little help from the nitrogen cycle. The nitrogen cycle itself is crucial for wildfire recovery. This is because fire releases the nitrogen from vegetation, which temporarily increasing its availability for new plant growth. But it also causes a net loss of nitrogen from the ecosystem. So how does that really work? Well, the ash from the fire adds nitrogen. Fire converts plant nitrogen into ash that enriches the soil with ammonium and nitrate. Microbes ramp up with fewer plants competing. Soil microbes are able to quickly use the ammonium and nitrify it into even more nitrate. And nitrogen-fixing plants move in, such as legumes and certain shrubs, and the most popular California native, the lupin. They will quickly colonize burned areas and pull nitrogen from the air thanks to the symbiotic relationship with bacteria, which adds more usable nitrogen to the soil. The extra nitrogen from the ash, the microbes, and the nitrogen-fixing plant species speeds vegetation recovery and jumpstarts ecosystem rebound, as you can see. So now to dive in on the importance of nitrogen and how it works within the nitrogen cycle. So nitrogen is essential for all life, but most organisms can't actually use atmospheric nitrogen, so therefore the nitrogen cycle is required. Nitrogen only becomes available to primary producers such as plants when atmospheric nitrogen is converted to ammonia through nitrogen fixation. Now, nitrogen undergoes many transformations within the cycle as organisms use the nitrogen for growth and energy, which also leads the nitrogen to change forms throughout the cycle and become available for other organisms. Major transformations in the nitrogen cycle include nitrogen fixation, nitrification, denitrification, and ammonification. These transformations are driven by diverse microorganisms such as bacteria, archaea, and fungi. Other drivers include decomposers like the aforementioned bacteria and fungi, lightning, volcanic emissions, and industrial processes. One of the first steps of the nitrogen cycle is nitrogen fixation. Atmospheric nitrogen is unavailable to plants and animals, even though it makes up 80% of our atmosphere. Nitrogen fixation is the process that makes it available by transforming it into ammonia. The strong triple bond between the nitrogen molecules in the reaction requires a lot of energy to break apart for the reaction. So because of this, there is only a small selection of specialized bacteria that are actually able to meet the high energy demand in order to make nitrogen fixation possible. The specialized bacteria that make this possible are sometimes free-living bacteria, where they're just living on their own, but most are actually part of a symbiotic relationship with nitrogen-fixing plants. They do this by living in the root nodules of plants such as the legumes, which are peas and soybeans, and other plant species. Some abiotic nitrogen fixation comes from lightning and some industrial processes. but most of it is going to come from the biological processes with the bacteria and the nitrogen-fixing plants. Now, ammonification is another process which converts nitrogen into ammonia and makes it available for plants. This is through organic nitrogen that is within the tissues of animal waste and decomposing organisms, where decomposers, such as fungi from before, break down the tissues and release inorganic nitrogen into the soil as ammonia, which then becomes available for the nitrification process. This ultimately is a vital role to regenerate nutrients in the soil, contributing to soil fertility and overall ecosystem health. Now, after either nitrogen fixation or ammonification occurs, the next step in the nitrogen cycle is nitrification. So nitrification is a two-step aerobic, which means that it needs oxygen, process, which means that the reactions in the steps need oxygen, which allows it to convert ammonia into nitrate, which is a more usable form of nitrogen for plants. The first step is known as ammonia oxidation, which is where bacteria oxidize ammonia to nitrite. These grow slowly because the reaction releases only a small amount of energy. Therefore, the bacteria that take part in this process make their own biomass using carbon dioxide, like plants do. But instead of sunlight, they use the ammonia. Now, step 2 is nitrite oxidation, which is where nitrite oxidizing bacteria, otherwise known as NOBs, oxidize the nitrite to nitrate. Like the ammonia oxidation process, this results in very little energy, which leads to the bacteria needing to oxidize as many nitrite molecules as they can. Some examples of NOBs, or nitrite oxidizing bacteria, are bacteria known as Nitrospira, Nitrobacter, which you can see in the slide photo, Nitrococcus, and Nitrospina. In the reaction, hydrogen ions and electrons that are observed they play a fundamental role in how nitrifying bacteria get energy from inorganic nitrogen compounds, and the release of the hydrogen ions is actually an inherent part of the chemical transformation of ammonium to nitrate. Now, the final step in the nitrogen cycle is called denitrification, which is an anaerobic, which means no oxygen needed, process that converts nitrates back into nitrogen gas and returns it to the atmosphere. This ends up balancing nitrogen fixation and prevents excessive buildup of reactive nitrogen in our ecosystems. It often takes place in low oxygen conditions in areas such as saturated soils, wetlands, and the anoxic zones of lakes and oceans, by anaerobic bacteria and some other microbes as well. In Monrovia, the nitrogen cycle isn't just happening in a distant forest. It's actually happening right above our homes in Monrovia Canyon Park. When the Bobcat Fire burned through our hills, it didn't just scorch trees. It disrupted how nitrogen moves through our soil, plants, and streams. And those changes flow downhill into the places where we live. As the canyon slowly recovers, new plant growth and restoration efforts are helping rebuild that nitrogen balance and support the return of native ecosystems and wildlife. By understanding this connection, our community can make smarter choices about how we care for our yards, our air, and our canyon. In the end, the nitrogen cycle here is really the story of how Monrovia is damaged, heals, and becomes more resilient after fire.